This is the second in a series of videos about dissolution. In the first video, we talked about the different types of solutions, what phases they were, what the solute and solvent were, and now we're going to get into the steps of dissolution and the enthalpy involved. Okay, so let's review what we know about bonds from our intermolecular forces in the last chapter. So we know that if we want to break a bond or some sort of an interaction, we have to break an interaction that's favorable, and so we have to put in energy to make that happen. It's like hitting it with a hammer. You have to put in energy to break a bond. So breaking bonds is going to be an endothermic process. Energy goes in. And if we want to do the opposite, if we want to form a new bond or a new interaction, being bonded is a favorable state. So the atoms or the molecules want to come together and want to form that interaction or that bond, that association together. So these are going to be like two magnets jumping together. It's going to actually release energy because it's so favorable to reach that final state. So forming bonds is exothermic, releases heat. So now let's look at the 3 steps of dissolution, knowing what we know about energy input or output. So what we have to do when we dissolve things is we first have to create space. So we have to expand each of the pieces. So first we're going to expand our solute, the smaller piece. So we could say we have a little bit of solute, not that much. And those particles are going to be associating together with intermolecular forces. And what we need to do is we need to break those interactions by putting in energy to spread them out. So there's space for that solvent to be in between those molecules. So we are going to break solute with other solute intermolecular forces. They're holding those like things together, and this is going to be an endothermic process. Okay, so we spread out our solute, and so now we have to spread out our solvent. We need to create space for that mixing to occur. All right, so this time, the bonds we are going to break are going to be between solvent molecules and other solvent molecules. And every time we break a bond, it's going to be endothermic. So if we were to draw a picture, we'll make this a bigger container because there's going to be much more solvent than solute. So we'll say we have this big container of liquid and it has particles fairly close together in it. And then here we'll separate them and we'll create more space. There's room to put solvent molecules, solute molecules in between. All right, and our final step, now that we've created space here and we've created space here, is to mix them together. So we'll mix solute and the solvent. And this time, we are not going to be breaking any interactions, we're going to be creating them. We're going to be creating interactions between the solute and the solvent. New intermolecular forces are formed. And new intermolecular forces are favorable, so the process is going to be exothermic. And there's a name for this step of the process. You might see it in your book. It's called solvation. I could make a really terrible joke about Christianity and our Lord and Solute, but I won't. Okay, so in this step, we're going to take two things and add them together. And remember that we created space, so these are pretty spaced out. And these are pretty spaced out. And so our final solution is going to look like some very spaced out red dots with blue dots all around them. So the solvent surrounds the solute in the solution to dissolve. So there's three major steps: the separation of each of the two pieces and the bringing of them together. And so let's talk about the enthalpy, or the energy needed for each of these processes, because some of these are positive steps and some of these are negative steps, and we want to know about the total enthalpy of the entire process. So our three steps: step one was separating the solute. Step two was separating the solvent. And step three was mixing them together. And what we know, because enthalpy is a state function, as we talked about in the last chapter, if we add together each of the individual steps, that change in enthalpy is equal to the total change in enthalpy, the total needed for dissolution. And so we know some information about these pieces. We know that this piece is positive and this piece are positive because these are breaking bonds. We know this piece is negative because this is forming bonds, but we don't know about the total, right? Whether this total piece is positive or negative depends on the size of these pieces. If these positive pieces are very large, the delta H total will also be positive, but if the negative piece is the largest, then the delta H total could be negative. So both of those are possible. So let's look at each of those situations and see what our diagram would look like. So let's make an enthalpy diagram like we did in our state law discussion, our state function discussion. And let's put in our initial enthalpy right here. So let's do the solute first. So the solute is always going to be a positive step. So expanding the solute is positive. And then if we expand the solvent, that one is also going to be positive. Make that line a little longer here. Okay, expanding the solvent. And then we need to mix the two together, and that's going to be an exothermic. So let's put that final line here. And this is going to be our enthalpy of mixing. So if you think about adding these together in order, if we started here at initial and we went to more positive enthalpy, to more positive enthalpy, and to more negative enthalpy, and we finished here, our total delta H for the entire process is going to look like this. And we can see that that arrow is pointing down. So this is going to be an exothermic delta H total. So the total energy resolved to dissolve this particular compound is going to be exothermic. And so we learned an interesting thing about these endothermic steps. We know that endothermic steps are generally unfavorable and exothermic tend to be more favorable. But we can still make those unfavorable steps happen. So unfavorable reactions, endothermic reactions, like breaking these intermolecular forces, these can still occur when they're paired with significantly exothermic steps. Right? Not just any exothermic step, a significantly exothermic step, which is a favorable step. And this is really one of the driving forces of science. This is one of the main tenets of biochemistry. If you ever go into the medical field or if you ever take that course, you'll find that all kinds of endothermic processes that happen in your body that shouldn't be favorable are possible because they're paired with an exothermic step. Okay, let's look at our other situation. So let's put our starting energy at the same point. And let's do our first step of the solute, but let's say it's a little bit bigger this time. Let's say you have to put in quite a lot of energy to separate the solute because maybe the intermolecular forces in this compound are particularly strong, so more energy is needed. And we have some pretty strong energy needed in this case to separate and expand our molecules of solvent. A little longer. And then let's say that the amount of energy released when they mix together is this much. This is supposed to be a straight line. Please excuse my art. Delta H of mixing. So here's our H final. So if we follow the path from initial to final, we start here, we go to higher enthalpy, lower enthalpy, and finish here. So the net journey was this. There's our total enthalpy. And you can see that this picture looks different. Our total enthalpy is a positive number. This is an endothermic total dissolution rate, enthalpy. And it's positive. And so now we feel like we're at a standstill, right? We've said we can pair endothermic with exothermic things to make them favorable, but we've added everything together. We've paired endothermic with exothermic, and we still ended up with endothermic. So what can we do? There is actually a concept we are going to talk about in the next chapter that's responsible for this, and it's called entropy. You may have recognized that. It's represented with an S, and entropy is how disordered the system is. A more disordered system is more favorable than a very ordered system. So the last trick left in our bag is if we have an endothermic overall reaction, if it produces something that's more disordered, it can still be favorable. So let's add that to our conclusions here. So endothermic, those are the unfavorable reactions, conditions. Unfavorable. So another way that we can make these occur is by increasing the system disorder. When they increase system disorder, which is called entropy, this is a favorable state, and they can still happen. Okay, so our mechanisms here are pairing with something significantly exothermic or increasing the disorder. Those are the ways we can make endothermic steps more favorable. So that is what you need to know about the enthalpy of dissolution and the different steps of dissolution. In the next video, we're going to talk about solubility of one solute into a solvent.